Today's objective, again, students will factor out, I believe that's supposed to be a T. Students will factor out GCFs, or greatest common factors. They'll factor trinomials, perform bottoms-up factoring, factor by grouping, factor difference of squares, sum of difference of cubes, factor expressions that have a quadratic nature in order to eventually factor expressions that require multiple steps. We'll probably just factor today. We probably won't go into anything else. I just want to focus the rest of the class period today on just plain factoring. So let's get started. I'll stop here for just a second because this is always your steps for factoring. Step number one, always look to see if there's a common factor. And when I mean common factor, let's apply it to simpler terms. If you have a 3, a 6, and a 9, a common factor, well, all of those contain 3's. If you have an 8 and a 12, those two numbers both contain 4's. Okay, looking for a number that will divide into both terms. If you have an x to the third and an x to the fourth, a common factor, both of those have 3 x's. One of them's got more, but they both have at least 3 x's. Next step, once you've seen is there a common factor, you'll move on and say, okay, is there 2 terms, is there 3 terms? If there are 2 terms, we'll check to see, do we have a difference of squares situation, or do we have a difference or sum of cubes situation? If not, we're done. If there are 3 terms, we'll see, is this a perfect square trinomial? Is it factorable trinomial? And we'll talk about what it means to be factorable in a second. And these two kind of go together. Is it factorable? And if so, are we going to have to use bottoms up? And then the last step is if it's not 2 terms, it's not 3 terms. If it's 4 terms or more, we'll check and see if we can actually factor by grouping. And eventually, as well as factor by grouping, we'll see, could we possibly use, I should put, or synthetic division. We'll either use factor by grouping or synthetic division if there are more than 3 terms. Here we go, first problem. So again, first step, ask yourself, is there any common factors? Is there anything that is common to all, in this case, 3 terms? As far as numbers go, you have a 9, a 6, and a 12. Colby, is there any numbers located in 9, 6, and 12, the same common number? What do you think? 3. All 3 of those numbers contain a 3. The terms contain x to the fourths, x to the thirds, and x to the seconds. Again, you ask yourself, is there anything in common? All 3 terms have at least 2 x's. So what we're going to do, we're going to use reverse distributive property here. We're going to pull out 3x squared. We're going to, in essence, kind of simplify this a little bit. And the way we do that, we ask ourselves, 3x squared times what would give me 9x to the fourth? Help me with that, Anne-Marie. 3 times what gives you 9? Good. And x squared times what gives you x to the fourth? Good. There's your first term. Then we say 3x squared times what gives me 6x to the third? Help me with that part, Trevor. 3 times what gives me negative 6? Good, negative 2. And x squared times what gives you x to the third? Perfect. And then I'll do the last one. 3x squared times what gives me 12x squared would be simply 4. Don't put any more x's with it. If you put another x with it, all of a sudden it'd be x to the third or x to the fourth. So that's my first step. Always see if there's anything common that can be factored out. And for now, we'll stop there. I'll go into bottoms up here in just a second. Okay, common factors, Allie. X squared y, 10xy, and 25y. As far as numbers go, Allie, 1, 10, and 25, is there anything common to all 3, not just 2 of the 3? No. A lot of people want to look at this, though, and see 10 and 25 and say, oh, there's a 5 in common. It must be common to every term. Okay? What about x's, Allie? Do all 3 of them have x's? No, but they do have y's. So help me, Allie. Pull out a y. Y times what gives me x squared y? Good. Y times what gives me 10xy? 10x, right? And y times what gives me 25y? 25. And for now, again, we'll stop. We might come back to this problem in just a second and finish it because there would be another step. Step number 1, see if there's anything common that can be factored out of all terms. What about this one? Negative z minus w. This little trick that I'm about to show you, you're going to use a good bit. You can pull out a negative there. It's kind of like pulling out a negative 1. Negative 1 times what is negative z? That'd be positive z. Negative 1 times what is negative w? That'd be positive w. So pulling out a negative there, in essence, pretty much just makes both of them positive. But here's a trick I really want to show. Let's do 3 minus x. Normally we wouldn't say really that anything is factorable here. Okay, 3 minus x, there's really nothing in common. But let me show you a trick that you're going to be using again for the rest of this semester, and let's go ahead and address it today, and then we'll talk about it again later. If I do factor out a negative here, Jordan, negative 1 times what gives me 3? Close. Negative 3. Everybody see that? Negative 1 times negative 3 would be that positive 3. Negative 1, Jordan, times what gives me minus x? Plus x. Good. So what that did actually, when I pulled the negative out, let's rewrite this. X is positive, 3 is negative. Look where you started and where you went. You started with 3 minus x. When you pulled a negative out, you were left with x minus 3. So if you ever have subtraction and for some reason you need to switch those two things, instead of x minus 4, you need 4 minus x. Instead of a minus b, you need b minus a. The way that you obtain that is by factoring out a negative. Factoring a negative out of a subtraction of binomials will flip-flop those two terms. Okay? You will use that. Actually, probably today. Okay, next up, let's go ahead and talk about, this would be factoring by grouping. Factor by grouping. And the hardest part about this, honestly, is recognizing which one you need to perform. And let me explain why we're going to use factor by grouping here. Number 1, there's no term that's common to all of them. X to the third, x to the second, x, no x's. 3 and 3, no 3s. Okay, no 6s, no 9s, no multiples of 3. So there's nothing you can pull out of all 4. There's not 2 terms, there's not 3 terms. So really this goes down to that very last step. If there's more than 3 terms, see if you can factor by grouping. First step, factoring by grouping, is to group a couple of them. Let's group the first 2, group the last 2. Just group some of them together. And then factor something common out. We group the first 2, group the last 2. Okay, look at these first 2. Is there anything in common? Brianna, what do you think? Anything in common between these 2 terms? How many x's? Well, how many do each of them have? This one has at least, they both have at least 2 x's. That's what we're pulling out. Okay, is at least 2 x's. And we do the exact same thing we did a while ago. Per group, x squared times what gives me x third would be an x. X squared times what gives me x squared would just be 1. That 1 is extremely important. Don't forget to put it. Ask yourself this. If I were to multiply this back out, would I obtain this again? Yes. If I had not put the x there, if I multiplied it back out, I would not have got x to the third plus x squared. You have to have the 1. This is this plus sign. 3x plus 3. Abby's absent. Caleb Haynes, what's common between 3x and 3? Just the 3. Good. Let's factor out that 3. Ask yourself the same question. 3 times what gives me 3x would be x. 3 times what would give me 3 would be plus 1. Okay, now you've got 2 different terms. You've got this underline x squared times x plus 1, and you have 3 times x plus 1. Out of the 2 terms, do you see what's in parentheses is common now? Both of these terms have an x plus 1 in it. So watch what I'm about to do. We're going to take this x plus 1 and we're going to factor it out. And this is kind of odd because normally you're factoring out things like 3's or x's or x squared or y to the thirds. But here you're going to factor out a binomial. This term has the binomial x plus 1. This term has the binomial x plus 1. Now listen real close to how I'm about to ask this question. X plus 1 times what gives me this? Well, here's x plus 1. X plus 1 times what gives me this term? X squared. X plus 1 times what gives me this term? Plus 3. Factor my group. Let's look at just that second step again. Let me show you two more problems that look like that. Rewind. Sometimes in these higher math courses, your terms don't just look like 2xy or 3x squared y to the third or something like that. This is a term. The reason this is a single term is it's stuff being multiplied together. Here's your plus sign. That's what splits the terms. And then you've got stuff being multiplied together, x to the third times x minus 5. And we're looking for common terms. Man, this is a whole lot harder than I needed to be. Put a y there, please. Make this a little bit easier. That would have been slightly confusing. And again, you look at these two terms and you see what they have in common. Both of them have, if you're left with, or if you've got a problem like this, it's actually easier than the other ones. Both of these have an x minus 5. When you pull x minus 5 out of this term, you're left with x to the fourth. When you pull x minus 5 out of this term, you're left with plus y to the third. That's how you factor those. Okay. My pen's not writing really good today. So are y'all okay that y'all understand if you're left with a binomial that can be pulled out, pull it out. Yeah, that's the moral of the story. Next one, another one of these. Factor by grouping group AW and BC and group BW and AC, and look at that. Dalton, AW and BC, is there anything common there? No. So that was pointless. Right? Any ideas? Let's do that. Let's rewrite this thing and write it as A and W, like the root beer, minus B and W, plus BC, minus AC. Does that look better now? When you're factoring by grouping, sometimes you might have to move the terms around and then group to where you can pull something out. Reminder that terms are movable as long as the plus and minuses stay in the right place. BW was negative, so it stayed negative. AC was negative, so it stayed negative. Now help me, Savannah. A and W and B and W. What's common? Good. Pull it out, and Savannah, what are you left with? Here and here. A minus B. Everybody good there? Avery's second set. What's common? Good. Pull it out. What are you left with? Remember what I told you a while ago? Something's wrong there. I'm looking for something now. I've got two terms. And when you factor by grouping, here's what you do. You, again, group them. You pull out what's common. And hopefully what's in parentheses will also be common. Now, look at those last problems. What was in parentheses was an x plus 1 and an x plus 1. That's the reason we could pull it out, because it was the same common term. Down here I had an x minus 5 and an x minus 5. I pulled it out front because it was common. Here, there's nothing common. I have a minus b and b minus a. and what I told you a while ago. Sometimes you might have to switch these things around. How can I do that? Pull out what else? A negative. If I pull out a negative, and I don't care for you just knowing this, instead of having to go through the work of it, pull out that negative, and that B minus A will turn into A minus B. Because again, the negative A will now turn into positive A. The what used to be positive B will now turn into a negative B. So it flip-flopped it. Now we have something common. Logan, we have again two terms. Here's one term, here's another term. They have A minus B in common. Logan, when I pull out A minus B, what am I left with in each of those terms? Perfect. Final answer. A minus B times W minus C. As you're finished writing that down, I just want to show you that you can check these. You don't have to write this unless you just want to in your notes. But what we did last night is how you check them. This is FOIL. A times W is AW. A times C, that's A times negative C, is negative AC. Negative B times W is negative B times W. And negative B times negative C is a positive B times C. We just factored. Factored in FOIL, opposites. Any questions? Okay, now, been there, done that several times. This is quadratic. Okay, again, if we go down through our steps, first step, look and see if there's any common factors. There's not. Okay, there's nothing that all three terms share. Second step is look and see how many terms you have. If you have two terms, we're going to try to factor by difference of squares or difference of sum of cubes. That's not two. There are three terms here. If there are three terms, here's what you're going to do. A 1 out front is simply two sets of parentheses. What multiplies give me x squared. You've seen this, right? And then we ask ourselves two questions. I need two numbers, which will go here and here. And those two numbers need to add to give me negative 5. And those same two numbers need to multiply to give me negative 14. Now, Ms. Green and I teach this slightly different. She teaches the whole look at the sign, and I don't care. Work it either way. Okay, whatever you're comfortable with. She teaches it, look at the sign here. If this is a negative, then you'll have a plus and a minus. If this is a positive, then you'll look at this sign, and if whatever this sign is, then if it's negative, they'll both be negative. If it's positive, they'll both be positive. Here's how I teach it. If this is a negative 14, and we've got to multiply to give me negative 14, can they both be negative? No. Can they both be positive? No. Just use your common sense. Just use your rules of positives and negatives. If it multiplies to give you negative 14, obviously one of them's got to be negative, one of them's got to be positive. That's the only way you can multiply to give you a negative. If we need to multiply to give us a negative 14 and add to give us a negative 5, what are the only things that multiply to give you 14? 2 and 7 and 1 and 14. And again, we know that one of them has to be negative. And how are we going to add to give me a negative 5 would be a negative 2 or negative 7. Negative 7, positive 2. Done. No. That's fine. Multiplication is commutative, so you can list either one first. What else was I going to say? Oh, I want you to start thinking of it like this. X squared, hopefully you remember. X squared is a parabola. Pretend like that's a parabola. What you just did is you split a parabola into a line times a line. Okay, a parabola is the product of two lines, right? Y equals mx plus b. Slope of 1, y-intercept of negative 7. Slope of 1, y-intercept of 2. Okay. Next one. Same thing. Two sets of parentheses, x and x. Multiplies to give me negative 21, adds to give me 4. Tootin, you want to help me with that? What multiplies to give me 21? Good. And we need a negative, so one of them we know has got to be positive, one of them's negative. So which one's going to be positive, which one's negative, Tootin? Positive, negative 3. And going back to 6th, 7th grade math, let me show you how I teach this. When you're having to add these things together, you have $7. You owe $3. If you plus 7, if you have 7 and you owe 3, then obviously really you just have 4 because you paid off those $3. If you needed a -4 there, obviously you had more debt than you have money, so you'd flip-flop those positives and negatives. Another one, wow. And again, like I said, I don't teach rules. I just use positive negative rules because I've already taught those. Or somebody taught y'all somewhere down the road. I need to multiply to give me a positive 6. There's two ways that you can multiply to give you a positive 6. That's either a positive times a positive or a negative times a negative. But you have to add to give you a negative. So obviously, it's going to be two negatives. Okay, use your rules of positives and negatives. To multiply to give you a positive and to add to give you a negative, they both must be negative numbers. Elizabeth, give me some ways to multiply to give you 6. 3 and 2 or 1 and 6, right? That's it. Okay, that's the reason I always start here because the list is so much shorter. So multiplying to give me 6, adding to give me a -5, I'd probably use the 2 and 3, right? And like I said before, they both must be negative because we need to add to give me a -5. And multiplying a negative times a negative does give you that positive 6. And I'm not saying solve. This is not an equation. I'm simply saying factor. Just breaking apart is all we're doing here. Okay, bottoms up. If there is a number out front, you're going to use what's called bottoms up factoring. Bottoms up factoring. Step number 1 in bottoms up. If there is a number, and this is the only time you have to use bottoms up factoring. If there is a number out front in front of the x squared, move it to the end. Multiply it times this last number. This problem has now turned into x squared plus 5x plus 4. Okay, let me kind of put an asterisk there and kind of talk about something. What I just did is completely illegal in mathematics. There is no rationale, there is no reason you can just do that. You can't be solving a problem and say, you know what, I think I'll move this number from here to the end. You can't do it, okay? This is a shortcut. There is no reason behind what I just did. Somebody tried it one time, it worked, and they went with it. Okay? That is not legal. Next step, factor this like we just did. Okay, because I would much rather factor x squared plus 5x plus 4 than to factor this junk. Two sets of parentheses, x and x, adds to give me 5, excuse me, multiplies to give me 4. Brett, what are those two numbers? Good, plus 4 and plus 1. Don't make the mistake I make, though. I'm terrible about circling that and thinking I'm done because I'll forget I'm working a bottoms-up problem. It's like, okay, bam, right answer, moving on. We're not finished, okay? Because if you multiply this back together, you're not going to get this. That's your check. Since this is a bottoms-up problem, what you do next, the number that you move, once you hit this point, the number that you moved, which was a 2, you will divide each of these numbers by. Again, there's absolutely no rationale behind that. Somebody tried it, it worked, we went with it. It's crazy. Not legal. If it will divide, like 4 and 2, that'll divide. Go ahead and divide it. 4 divided by 2 is 2. If it will not divide, 1 and 2, that won't divide. A lot of people say, yeah, well, it's 2. No. 1 and 2, it'll give you a decimal. 1 divided by 2 is 0.5. If it will not divide evenly, try to reduce it. It won't reduce either. Okay? So we leave it. And this is where this thing gets its name. If it's on bottom, move it up to the front. Done. Bottoms up factor. And you can check that. X times 2x gives you 2x squared. X times 1 is x, 2 times 2x is 4x, x and 4x gives you 5x, and 2 times 1 gives you 2. Bottoms up. Next problem. 6x squared minus x minus 12. Always look for common factors. There are none. Since there are no common factors, since it's a quadratic trinomial, we're going to factor by grouping. Or we're not factoring by grouping. We're going to factor by two sets of parentheses. Move this to the end since there's a number out front. Now have x squared minus x minus 6 times 12 is 72. I do that because I'd rather factor that. Just to give you a preview, I talked about trial and error a while ago. To give you a preview of what trial and error look like, and you don't have to write this down, it's just scary, don't do it. What you would do is you'd try to come up with two things like maybe 2x and 3x that multiplies to give you 6x squared. Then you'd come over here and try to come up with two things that multiply to give you negative 12, which is like a negative 3 and a positive 4. That's my trial. What do I do now? You multiply it back out together to see if you get this. If you don't get this, you try something else. And you keep trying other stuff until, which is probably the way that y'all worked in the past, and you keep trying stuff until you find something that multiplies to give you that. Now, one positive about this is you get really good at FOIL, because you might have to FOIL out 5, 6 different times in the same problem just to see, do I get this answer? But we're not doing it like that. X and X. Daniel, what multiplies? Give me a list of things that multiply to give you 72. What's the most obvious one? 6 and 12 and 9 and 8. And since 9 and 8 have, because it's negative 72, since 9 and 8 have a difference of 1, that's what we're going to use here. A negative 9 and a positive 8. Adds to give you negative 1, multiplies to give you the negative 72 that you need. And again, don't circle it. You're not done. Bottoms up. Okay? Had the number out front. Again, if the number got moved, let's divide it back. This is a good one. When you go back to study, I would probably look at this one as opposed to the one we just worked. For this reason. This will not divide. This will not divide. If they will not divide, do not forget to reduce them. 9/6, Noah, what does that reduce to? Good. And 8/6, what does that reduce to, Skylar? Good. Now that we reduced them, now bottoms up. Okay. Divide it, reduce it, bottoms up. What's on the bottom, put it up front. So that'd be a 2x minus 3. And this will be a 3x plus 4. Oh, look at that. Check that out. I'm the lucky friend. But like I said, there was, you could have tried 2x and 3x. You could have done minus 2 and plus 6. You could have done minus 3 and plus 4. You could have done minus 4 plus 3. Instead of 2x and 3x, you could have done 6x and 1x. There's several different combinations there, and the chances of you getting it right the first time, unless you're me, is like probably 5%. You know, but I amaze people like that. Okay, that was if there are 3 terms. Now I think this is the final one. What if there's just 2 terms? If there's just 2 terms, you're very limited on what you can do. First thing, of course, look and see if there's anything common. Here there's not. 4 and 1, nothing there. X squared, no x's, nothing there. First thing you look at beyond that is, do you have a difference of squares? And let's review real quick. X plus 3 times x minus 3. What did we call those, Lydia? Conjugates. And when we multiplied conjugates together, we didn't have to worry about our middle term. X times x was x squared. Positive 3 times negative 3 is negative 9. Look what that multiplied into. A perfect square. X times x is x squared. 3 times 3 is 9. Both of those I can find the square root of. This is what we call difference, bless you, difference of squares. Difference of squares will always factor back into conjugates. We like these problems. Difference, 2x times 2x, 1 times 1. Perfect squares. So it factors into 2x times 2x, Positive 1, negative 1. Done. Conjugates. If you don't believe me, conjugates, if you multiply them back together, 2x times 2x gives you 4x squared. Positive 1 times negative 1 gives you negative 1. Difference of squares will always factor into conjugates. And this one's hard to recognize sometimes, but honestly, you don't really have to recognize it. You can factor this one like normal, but if for some reason you want to try this, if you're able to take half of that middle term and square it and give you the last term, this is what's called a perfect square trinomial. A perfect square trinomial, PST. And I'm just going to briefly talk about this because honestly, you know what, I'd factor it like this anyway. But I do want to point out the relationship here for future reference when we start completing squares. I want you to at least heard the term before, perfect square trinomial. X times x is x squared. Multiplies to give you 9, adds to give you negative 6 would be a negative 3 and a negative 3. What we mean by a perfect square is, well, look, it factored into 2 of the same thing. So you could actually write that as x minus 3 squared, 2x minus 3s. Again, the way that you can recognize to see if something is a perfect square trinomial, if you can half this and square it, and it gives you this, it's gonna factor out like that. Half of negative 6 is negative 3. Negative 3 squared is 9. Oops. X squared, another example of that, x squared plus 10x plus 25. Half of 10 is 5. 5 squared is 25. That would factor into x plus whatever half of that was. So if you can recognize it, it's pretty quick to factor them. But again, you don't have to know that. You do not have to know that this factors into a perfect square. We'll hit that again later. Just wanted to show it to you real quick. Same way here, honestly, I'd factor this by bottoms up. We're not going to go through this one. Move the 9 to the end. This one also is a perfect square because of if you move the 9 to the end and do 9 times 225, well, half of this, which is 15, 15 times 15 is 225. So you've got a perfect square trinomial there. Again, we're not going to go there. This is another difference of squares. There's 2 terms. What multiplies times itself? That's the hard part here. What multiplies times itself to give you x to the 2t power? Let's try x to the t. X to the t times x to the t. Well, if it was x squared times x squared, you'd add these together, so let's add them together. T plus t is 2t. That's right. So here you go. 2 sets of parentheses. Difference of squares factors into conjugates. That'd be x to the t and x to the t plus 3 minus 3. Even works for that. I believe last thing we're doing before we put it all together, difference in sum of cubes. Here's your formulas. I'll go ahead and give you formulas for these. Here's your formulas for difference of cubes, sums of cubes. If you've got like a perfect cube, a to the third minus b to the third, and that could be like x to the third minus 27. X times x times x. 3 times 3 times 3. That's what I mean by a cube. Something that multiplies by itself 3 times. We can use these formulas. So I'll give you a second to write them down. First problem. X to the third minus 27. That fits this first formula. Stuff to the third minus stuff to the third. And let me show you how easy this is. Guys, first identify what, instead of a to the third, you have x. So your a value in your formula is x. Your b value in your formula. What number are we raising to the third power there? 2 to the third, 2 times 2 times 2 is 8. 3 to the third, 3 times 3 times 3, that is 27. So in my formula, my b value there, instead of b to the third, it is 3 to the third. That right there is the hardest part. If you can do that, you're finished. If you can identify what's being raised to the third here, what's being raised to the third here, which is what I just did. My a value in my formula is x. My b value is 3. Now what do? I take this formula. Everywhere I have an a, I put an x. Everywhere I have a b, I put a 3. Done. So this factors into a minus b times a squared plus a times b plus b squared. Finish. Difference of cubes. Okay, again, this is sum of cubes. The reason it's sum of cubes, 2 times 2 times 2 gives you 8. 5 times 5 times 5 is 125. W squared times W squared times W squared is W to the 6th. Z times Z times Z is Z to the 3rd. So this is, okay, my A value and my B value. What am I raising to the 3rd power? We're on this one now. What am I raising to the 3rd power to give me this first term? That would be a 2W what? Good. Somebody said it over here. Raise it to the 3rd power, you get an 8. Raise this to the 3rd power. Power to power, you multiply. So that's 8W to the 6th. Oops, why am I putting that on B? Getting ahead of myself. A is 2W squared. B is what am I raising to the 3rd power to give me this? That would be a 5W. 5 times 5 times 5 is 125. Can't think straight. 5Z. 5 times 5 times 5 is 125. Z times Z times Z is Z to the 3rd. So again, take your formula. Everywhere you have an A, put 2W squared. Everywhere you have a B, put 5Z. Uh-oh, we got a square A. Help me with that part of it, Colby. A to the 2nd power. This stuff to the 2nd power would be, good. And then minus A times B would be 10 alphabetical order W squared Z. And then we got a square B. Anna Marie, square B for me. 5Z to the 2nd power is good. And that's as far as you can go.